every civilization that ever reached for the star stopped. That is not a theory. That is what the data is quietly, persistently telling us. But there is one explanation so dark, so uncomfortably specific, that most researchers hesitate before saying it out loud. What if the silence is not empty space? What if it is a graveyard? And here is a question. If you could teleport anywhere in the universe, where would you explore first? Let us know in the comments below. I will pin the most creative answer. Now let's begin. There are stars out there that formed 10, even 11 billion years ago, long before our sun was even a glimmer in the gas cloud that would eventually collapse into it. If any of those ancient stars had planets, then a civilization that emerged around one of those ancient stars would be so far ahead of us on the timeline that the entire history of human existence would look like the final second of a very long film. Think about what humanity has accomplished in just the last 200 years. We went from riding horses to landing on the moon, from sending letters by hand to transmitting information at the speed of light, from barely understanding germs to mapping the entire human genome. 200 years. Now multiply that rate of progress by 1 million, by 1 billion. A civilization with even a 10 million year head start on us should, by any reasonable expectation, be so advanced that their technology would look indistinguishable from magic to us. They should have colonized star systems, they should have reshaped galaxies, they should be everywhere, and yet nothing, complete silence. This is the heart of the paradox, and it is not a minor puzzle. It is one of the deepest, most disquieting questions in all of science. The Italian-American physicist Enrico Fermi supposedly captured it perfectly during a casual lunch conversation in 1950 with fellow physicists at Los Alamos National Laboratory. Someone at the table was talking about recent reports of UFO sightings, and Fermi, after a moment of thought, asked a simple question: "But where is everybody?" He was not being naive. He was pointing at a genuine contradiction. If the universe is this old, and this vast, and stars and planets are this common, then even a single civilization that developed interstellar travel millions of years ago should have had more than enough time to spread across the entire galaxy. Even traveling at a tiny fraction of the speed of light, say 1%, a civilization could cross the Milky Way in a few million years, and the Milky Way is over 10 billion years old. The math does not add up. Something is missing from the equation. Now, to really feel the weight of this paradox, we need to talk about what we actually know about planets and the likelihood of life. Because one of the biggest developments in the last 30 years of astronomy has completely changed how we think about this question. For most of human history, we did not know whether any other stars had planets at all. Our own solar system was the only example we had. Then, in 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of the first confirmed exoplanets, planets orbiting a pulsar called PSRB 1257+12. 2 years later, in 1995, Michel Mayor and Didier Queloz detected the first exoplanet orbiting a sun-like star, a gas giant called 51 Pegasi b. That discovery won them the Nobel Prize in Physics in 2019. Then came the revolution. NASA's Kepler Space Telescope launched in 2009 and stared at a single patch of sky for years, watching for the tiny dips in starlight that happen when a planet passes in front of its host star. What it found was staggering. In just that one small slice of the galaxy, Kepler detected thousands of exoplanet candidates. Scientists used those numbers to estimate that there are likely more planets than stars in the Milky Way, more planets than stars. That means hundreds of billions of worlds just in our galaxy alone. And many of those worlds sit in what astronomers call the habitable zone, the region around a star where liquid water could exist on a planet's surface. Water, as far as we know, is essential for life as we understand it. The James Webb Space Telescope, which launched in December 2021 and began its full science operations in 2022, has already begun studying the atmospheres of some of these worlds, searching for chemical signatures that might hint at biology. It is the most powerful space observatory ever built, and it is transforming our understanding of what alien worlds might look like. So planets are not rare. Habitable zone planets are not rare. And yet, despite all of this cosmic real estate, we have not found a single confirmed sign of another civilization. No radio signals, no laser pulses, no megastructures, no visitors, nothing. Which brings us to the central question of this video: why? There are many proposed answers to the Fermi Paradox, dozens of them in fact. Some are hopeful, some are deeply disturbing, some challenge our most basic assumptions about intelligence, technology, and what it means to be a civilization. But one family of explanations stands out as particularly haunting. It is the idea that there exists what some scientists call a great filter. The concept was introduced by economist Robin Hanson in a 1998 paper, and it goes something like this. Somewhere along the path from simple chemistry to a spacefaring civilization, there is a step that is almost impossibly hard to pass through. A filter. Something that catches and eliminates nearly every civilization before it can spread beyond its home system. The terrifying question is not whether the filter exists. The terrifying question is where it sits on the timeline. Is it behind us, or is it ahead of us? If the great filter is behind us, if the hard step was something like the origin of life, or the development of complex cells, or the emergence of intelligence, then we might be genuinely rare, perhaps even alone. In that case, we are the lucky survivors. We pass through the filter. The road ahead might be clear, but if the filter is ahead of us, if there is some catastrophic, near-universal fate that awaits every civilization that reaches our level of development, then the silence of the cosmos is not comforting at all. It is a warning. And here is the thing: the more we discover that life's building blocks are common in the universe, the more we find that planets are everywhere, that the chemistry of life arises readily, the more ominous the silence becomes. Because if the ingredients are everywhere, but the result is nowhere to be found, something must be stopping civilizations in their tracks. Something is filtering them out. What could that filter be? What could be so universal, so powerful, so perfectly efficient that it stops civilization after civilization from ever reaching the stars? That is exactly where we are going next. In the parts ahead, we will dig into the real physics of interstellar travel, the sobering math of cosmic distances, the psychological and biological limits of intelligent species, and the chilling possibilities that might explain why the universe looks so empty. We will talk about real missions, real telescopes, real data, and we will ask the questions that keep astronomers and thinkers awake at night, because here is the thing about this mystery. It is not just an abstract puzzle. It is about us. It is about our future. It is about whether the story of humanity ends here, around this one small star, or whether it stretches out into the cosmos in ways we have barely begun to imagine. You are made of atoms forged in the hearts of ancient stars, the calcium in your bones, the iron in your blood, the oxygen in every breath you take. All of it was cooked in stellar furnaces and scattered across space by supernova explosions billions of years before you were born. You are, in the most literal sense, a child of the cosmos, and the question of whether civilizations can escape their stars is ultimately a question about what that heritage means, about what we are capable of, about whether the universe is a place that nurtures intelligence or one that quietly, efficiently erases it. So stay with me. We are just getting started. Let us talk about distance. Because before we can understand why leaving a star system is so hard, we need to truly feel how far away everything is. And I mean truly feel it, not just intellectually acknowledge it. but viscerally understand it in a way that changes how you see the night sky. Our nearest stellar neighbor is a small red dwarf star called Proxima Centauri. It is part of the Alpha Centauri system, a grouping of 3 stars that sit closer to us than any other stars in the galaxy. How far away is Proxima Centauri? About 4.2 light-years. A light-year is the distance light travels in 1 year, moving at roughly 299 million meters per second, the fastest speed anything in the known universe can travel. In 1 single second, light crosses a distance of about 300,000 kilometers. In 1 year, it covers about 9.5 trillion kilometers. 4.2 light-years means that even light, the fastest thing that exists, takes 4 years and 2 months to make the journey from Proxima Centauri to Earth. 4 years at the speed of light. And we have never come remotely close to building anything that travels at the speed of light. The fastest human-made object ever launched is the Parker Solar Probe, which as of recent data has reached speeds of around 690,000 kilometers per hour as it dives close to the Sun. That is extraordinarily fast by any everyday standard. It is about 0.064% of the speed of light. At that speed, the fastest we have ever sent anything, it would take roughly 6,500 years to reach Proxima Centauri. 6,500 years. Human civilization as we know it, with writing, cities and agriculture, is only about 5,000 years old. We would need longer than the entire span of recorded human history just to reach our closest neighbor. And Proxima Centauri is right next door, cosmically speaking. The center of the Milky Way is about 26,000 light-years away. The Andromeda Galaxy, our nearest large galactic neighbor, sits at about 2.5 million light-years. The edge of the observable universe is roughly 46 billion light-years away in every direction. These numbers are not just big. They are, in a very real sense, incomprehensible to the human brain. Our minds evolved to track predators on the African savanna, to judge distances of a few hundred meters, to plan for the next season. We are not wired to intuitively grasp what 4.2 light-years actually means, let alone 2.5 million, but we need to try, because these distances are the first and most obvious candidate for our great filter. Maybe the reason that no civilization has ever left its star system is simply this. The universe is too vast, and the physics are too unforgiving. Now, here is where things get genuinely fascinating. Because physicists and engineers have not just shrugged at this problem, they have taken it seriously, done the math, and come up with real proposals for how interstellar travel might actually work. And some of those proposals are more credible than you might expect. The most straightforward approach is also the most humble. You do not try to go fast. Instead, you send something small, something that can survive for thousands of years, and you just wait. This is the concept behind generation ships, enormous spacecraft that would carry not just a crew but an entire self-sustaining civilization. People would be born, live their whole lives, and die aboard the ship. Their children and grandchildren and great-grandchildren, dozens of generations down the line, would be the ones to actually arrive at the destination star. It is a sobering idea. You would be asking people to commit not just their own lives, but the lives of every descendant they would ever have to a journey none of them chose. The ethical questions alone are staggering, but from a pure physics standpoint, it is not impossible. With a large enough ship, a reliable enough energy source, and a stable enough social structure, a generation ship could theoretically make the crossing to a nearby star over thousands of years. A more ambitious version of the same idea is suspended animation or cryogenic sleep, the concept of putting travelers into a state of dramatically reduced biological activity so they age very slowly or not at all during the journey. This is a popular idea in science fiction, but actual science is beginning to engage with it seriously. Researchers have studied torpor, a natural state of reduced metabolism seen in some animals, including certain bears and ground squirrels, and explored whether something similar could be induced safely in humans. A 2020 study published in the journal Neuron found that activating certain neurons in mice could induce a torpor-like state in animals that do not naturally hibernate, suggesting the biological machinery for it might be more universal than we thought. We are nowhere near applying this to humans for space travel, but the underlying biology is being examined with real scientific rigor. Then there are more radical concepts. The Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking and billionaire Yuri Milner, proposed something genuinely audacious, sending a fleet of tiny, gram-scale spacecraft, little more than a chip and a sail, to Alpha Centauri, pushed by an enormous array of ground-based lasers. The idea is that these laser-propelled light sails could reach speeds of around 20% of the speed of light, arriving at Proxima Centauri in roughly 20 years, not 6,500 years. 20. The engineering challenges are immense. You would need a laser array capable of delivering roughly 100 gigawatts of power. The sail material would need to survive the acceleration forces and the interstellar medium, the thin but not entirely empty soup of gas and dust between stars. The tiny spacecraft would need to survive for decades, transmit data across 4 light-years with almost no power, and somehow slow down when they arrive, since the laser array cannot push them from behind once they are gone. But the physics actually works. This is not science fiction. It is an engineering problem, which is a very different thing. But here is the catch, and it is a big one. Even Breakthrough Starshot, if it works perfectly, only gets a tiny piece of equipment to another star, not people, not a civilization, just a chip with a camera. For a biological species like us, warm, fragile, social, dependent on food and water and air and gravity, actually getting bodies to another star system is a challenge of an entirely different magnitude. Human beings are not built for space. And the longer we have been sending people into orbit, the more clearly we have understood just how badly the space environment breaks our bodies down. Astronauts on the International Space Station, which orbits Earth at an altitude of roughly 400 kilometers and is still very much within Earth's protective magnetic field, experience serious physiological changes even on missions of just 6 months. Bone density drops, muscles waste away, fluid shifts toward the head, creating vision problems that in some cases have led to permanent changes in the structure of the eye. The immune system becomes dysregulated. Sleep is disrupted by the station's 90-minute day-night cycles, but those are almost minor compared to what would happen on a true interstellar journey. The biggest threat is radiation. In low Earth orbit, the planet's magnetic field deflects much of the dangerous radiation streaming from the Sun and from cosmic sources beyond our solar system. Once you leave that protective bubble, you are exposed to the full fury of the cosmos. High-energy particles, galactic cosmic rays, stream through space from all directions, the remnants of supernova explosions and other violent events across the galaxy. These particles are capable of penetrating most shielding materials and passing straight through the human body, damaging DNA, increasing cancer risk, and potentially causing cognitive impairment over time. NASA data from the Mars Science Laboratory mission, which carried a radiation detector during its 8-month cruise to Mars in 2011 and 2012, found that astronauts on that journey would have received radiation doses equivalent to roughly 1.8 millisieverts per day. A round trip to Mars, roughly 1 to 3 years, depending on mission design, could expose a crew to radiation levels approaching or exceeding the career limits set by NASA for safety. And Mars is still inside our own solar system. It is still relatively close, still somewhat sheltered by the Sun's magnetic field. A journey beyond the heliopause, the boundary where the Sun's influence ends and true interstellar space begins, would be far, far worse. Voyager 1, launched in 1977, crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. It is currently about 23 billion kilometers from the Sun. That sounds enormous, and it is, but it is still less than 1,000th of the distance to Proxima Centauri. We have sent exactly 2 objects into interstellar space, Voyager 1 and Voyager 2, and they are barely off our front porch by cosmic standards, so the distances are brutal. The physics of getting there at any meaningful speed is punishing. The biological reality of keeping humans alive and healthy for journeys spanning decades or centuries is daunting. And we have not even talked yet about what happens when you try to stop, or land, or establish a colony, or survive long-term on a world that evolved without you. Every step of the journey is a potential filter, every single one. And yet here is what makes this conversation so profound. We are a civilization that is genuinely grappling with these challenges. We have the James Webb Space Telescope probing the atmospheres of distant worlds. We have the Parker Solar Probe diving closer to the Sun than anything before it, teaching us how stars work. We have serious engineers and physicists at institutions like NASA, ESA, Caltech, and MIT actively designing laser propulsion systems and radiation shielding and closed-loop life support systems. We are a species that, despite all of our limitations, keeps pushing at the boundaries of what is possible, which makes the silence even more striking. If we, in just a few hundred years of scientific progress, have already started seriously planning for interstellar travel, however far off it still might be, then a civilization a million years ahead of us should have cracked these problems long ago. The distances are the same for everyone. The laws of physics do not change depending on how smart you are, but a civilization with a million-year head start would have technologies we cannot even conceptualize. So either those civilizations exist and are staying silent for reasons we do not understand, or they tried and failed, or they never made it this far in the first place, or perhaps, and this is the thought that keeps some scientists up at night, there is something specific that stops civilizations right around our current stage of development, something that we are approaching right now without necessarily knowing it. That is where we are heading in the parts ahead. The great filter is waiting for us, and it may be closer than we think. But before we get there, I want to leave you with one image to carry into the next part. In 1990, as Voyager 1 was leaving our solar system, the late astronomer Carl Sagan convinced NASA to turn the spacecraft's camera back toward home for one final photograph. What Voyager captured was a single tiny dot of light, barely visible against the vastness of space. Sagan called it the pale blue dot. He wrote, "Look again at that dot. That's here. That's home. That's us. Everything humanity has ever done, every king and peasant, every act of courage and cruelty, every inventor and explorer, every teacher and dreamer, all of it happened on that dot. And from even the modest distance of 6 billion kilometers, it nearly vanishes into the background of space. Now imagine looking back from Proxima Centauri, from 26,000 light-years away at the galactic center, from 2.5 million light-years at Andromeda. From those distances, our sun is not even a pale blue dot. It is nothing. It is invisible. It is silence. We are alone in that silence for now. And the most urgent question of our time might be whether we stay that way. Let us talk about the great filter. Really talk about it. Because this concept is not just a thought experiment for philosophers. It is a framework that some of the most serious scientists and thinkers on Earth use to reason about our future. And once you truly understand what it implies, it changes the way you see almost everything happening in the world around you right now. Robin Hanson, the economist who formalized the idea in 1998, framed it with elegant simplicity. He looked at the Fermi Paradox and said, "Somewhere between dead chemistry and a galaxy-spanning civilization, there is at least one step that is so improbable, so extraordinarily difficult, that almost nothing makes it through. That step, or collection of steps, is the filter. And the single most important question we can ask as a civilization is this: have we already passed through it, or is it still in front of us?" To understand why this matters so much, think of the journey from a lifeless planet to an interstellar civilization as a long staircase. Each step represents a major transition in the development of life or intelligence. You start with a rocky planet in the habitable zone of a stable star. Then you need liquid water. Then you need chemistry, the right molecules forming in the right way. Then you need the first self-replicating molecule, something that can copy itself and pass on information. Then simple, single-celled life. Then complex cells with a nucleus, what biologists call eukaryotes. Then multicellular life. Then sexually reproducing organisms. Then animals with nervous systems. Then social creatures capable of communication. Then intelligence. Then language. Then tools. Then science. Then technology. Then someday the stars. Every single one of those transitions had to happen on Earth for you to be here reading this. And the question that haunts the great filter idea is, which of those steps is the one that almost never happens? Let us start with the most optimistic possibility, because it is important to understand what we would need to be true for the future to be bright. If the great filter is behind us, if it is one of the early steps on that staircase, then the universe could genuinely be nearly empty of other civilizations, not because something destroys them, but because life is extraordinarily rare to begin with. The hard step might be abiogenesis, the origin of life from non-living chemistry. This is something that happened on Earth, but we still do not fully understand how. We know the basic building blocks are everywhere. Amino acids have been found in meteorites. Complex organic molecules have been detected in interstellar gas clouds by radio telescopes. The Murchison meteorite, which fell in Australia in 1969, contained more than 90 different amino acids, most of which are not even found in living things on Earth. The ingredients for life seem to be scattered throughout the cosmos, but having ingredients is not the same as having a recipe. We do not know precisely how the first self-replicating molecule arose on Earth. We do not know whether it happened once, in one place, under one very specific set of conditions, or whether it was an almost inevitable consequence of chemistry given enough time and the right environment. If it was a 1 in a trillion fluke, then Earth might genuinely be the only place where it happened in our entire observable universe. That would be lonely, almost unbearably so, but it would also mean the filter is behind us. We are through the hard part. There is also the question of the transition from simple cells, prokaryotes, cells without a nucleus like bacteria, to complex cells with a nucleus, the eukaryotes. This transition happened only once in the history of life on Earth, about 1.5 to 2 billion years ago, when one simple cell essentially swallowed another and they formed a partnership that never ended. The inner cell became the mitochondria, the energy-producing organelle that powers every complex cell on Earth. This event, called endosymbiosis, was so improbable that some biologists argue it may be the rarest step of all. Bacteria have been around for at least 3.5 billion years. Complex cells appeared maybe 2 billion years ago. For 1.5 billion years, life stayed simple. Maybe in most places in the universe it never makes that leap. Maybe everywhere else, life is just bacteria forever. If that is the filter, then we are extraordinary. Not because we are special in some mystical sense, but because we are the statistical outlier, the 1 in a billion lottery winner, in the cosmic sweepstakes of complexity. But what if the filter is not behind us? What if it is ahead? This is where the conversation gets genuinely unsettling, and where we need to be honest about what the data is actually telling us. Because in recent years, some of the evidence has been quietly shifting in a direction that is not entirely comfortable. The James Webb Space Telescope has been finding that complex organic chemistry is even more widespread in the universe than we previously thought. In 2023, Webb detected carbon dioxide, methane, and water vapor in the atmosphere of the exoplanet K218b, a sub-Neptune world about 120 light-years away. This was not a detection of life, but it was a demonstration that Webb can actually read the chemical fingerprints of distant planetary atmospheres, something we could barely dream of a decade ago. If and when Webb or its successors detect something that looks like a biosignature, a chemical that should not be present without biological processes, the implications will be staggering. And here is the thing: if we start finding that life is common, that microbial life, simple life, exists on Mars or in the oceans beneath Europa's ice shell, or on some distant exoplanet, then the early steps on the staircase are clearly not the filter. Life gets started relatively easily, which means the filter must be somewhere further up the staircase, somewhere closer to where we are right now, and that is a deeply sobering thought. Because it means that whatever destroys civilizations, whatever stops them from reaching the stars, it happens at a level of development that we have already reached or are about to reach. It is not something that happens to bacteria. It is something that happens to creatures who have language, and cities, and technology, and nuclear weapons, and climate change, and artificial intelligence. Let us be specific about what those potential future filters might look like. Because this is not abstract theorizing. These are real risks, grounded in physics and biology, and the patterns of history that researchers actively study and write about in peer-reviewed journals. The first and most obvious is self-destruction through technology. We are, as a species, in the peculiar position of having developed tools that are capable of ending our civilization before we have developed the wisdom to use them responsibly. Nuclear weapons are the most obvious example. At the height of the Cold War, the United States and the Soviet Union together had tens of thousands of nuclear warheads, enough to destroy human civilization many times over. We came frightening close to using them in October of 1962 during the Cuban Missile Crisis, a crisis that, thanks to declassified documents released in later decades, we now know was even more terrifying than the public understood at the time. On October 27th of that year, a Soviet submarine called B-59, cut off from communications and under depth charge attack from American forces, nearly launched a nuclear torpedo. The only reason it did not was because one officer, Vasily Arkhipov, refused to authorize the launch. One man, on one submarine, standing between humanity and nuclear war. We survived that moment, but the weapons still exist, and nuclear weapons are not the only technology with civilization-ending potential. Advances in synthetic biology are making it increasingly possible for small groups, or even individuals, to design and engineer dangerous pathogens. The COVID-19 pandemic, which emerged in late 2019 and killed millions of people worldwide, was caused by a naturally occurring virus. The possibility of an engineered pathogen, one designed to be more transmissible, more lethal, or more resistant to treatment, is something that biosecurity researchers treat as one of the most serious risks of the coming decades. The National Academies of Sciences, Engineering, and Medicine and organizations like the Johns Hopkins Center for Health Security have published extensive analyses of these risks, and the consensus is not reassuring. Then there is climate change. Earth's average surface temperature has risen by about 1.1 to 1.2 degrees Celsius since the pre-industrial era, according to data from NASA and the National Oceanic and Atmospheric Administration. That might sound small, but the cascading effects, rising seas, more intense storms, shifting agricultural zones, increasing frequency of extreme heat events are already reshaping human civilization. The Intergovernmental Panel on Climate Change has warned that without dramatic reductions in greenhouse gas emissions, warming of 2, 3, or even 4 degrees Celsius above pre-industrial levels is possible within this century. At those levels, the impacts on human societies, food systems, and ecosystems could be catastrophic. None of these are guaranteed to end civilization, but each one represents a genuine risk. And the point that the Great Filter framework forces us to confront is this: every civilization that develops technology probably develops all of these risks more or less simultaneously. The same chemistry that gives you medicine gives you biological weapons. The same physics that gives you nuclear energy gives you nuclear bombs. The same industrialization that gives you global prosperity gives you climate change. These are not accidents. They are structural features of technological development, and if every civilization faces them, and if not all, or even most civilizations navigate them successfully, then the filter might be built right into the nature of intelligence itself. There is another possibility that is less dramatic, but perhaps even more probable, and it is one that does not get nearly enough attention in these conversations. What if civilizations do not destroy themselves? What if they simply stop? What if the drive to expand, to explore, to reach outward is not a permanent feature of intelligent life, but a brief temporary phase? Think about it this way. Right now, humanity is in a period of explosive outward expansion. We are launching telescopes and rovers and probes in every direction. We are building the frameworks for a return to the moon through NASA's Artemis program. We are seriously discussing crewed missions to Mars. There is an energy to our exploration, a hunger for the new, that feels like it could carry us to the stars. But will that always be true? Consider how technology is reshaping what it means to be human right now. In the early decades of the 21st century, virtual reality environments are becoming increasingly immersive. Social media and digital entertainment are engineered deliberately by teams of expert psychologists and engineers to be as engaging as possible, to hold your attention for as long as possible. What happens when those technologies become truly indistinguishable from physical reality? What happens when you can live in a simulation that feels exactly like the real world, but is perfectly tailored to make you happy, comfortable, and endlessly entertained? Why would you leave? Why would you choose the cold, dangerous, centuries-long ordeal of interstellar travel when you could stay home and experience whatever you wanted, instantly, perfectly, without risk? This idea, sometimes called the simulation hypothesis, or in the context of the Fermi Paradox, the Lotus Eater hypothesis, suggests that advanced civilizations might simply turn inward. Not destroyed, not failed, just content, choosing comfort and virtual experience over the brutal challenge of physical space exploration. It sounds almost peaceful, but the result in terms of the observable universe is identical to extinction. A civilization that retreats entirely into virtual experience disappears from the cosmos just as completely as one that blows itself up. The stars remain empty either way. And here is the thread that connects all of these possibilities: the self-destruction, the technological risk, the retreat into comfort and simulation. They all share one feature: they are filters. They are places on the staircase where civilizations stop climbing, where the universe's long experiment with complexity and consciousness reaches a ceiling and goes no further. The question that matters, the question that is, in a very real sense, the most important question our civilization faces, is whether we can see the ceiling coming before we hit it, because awareness is the first step toward avoidance. You cannot navigate around an obstacle you cannot see, and there is something deeply hopeful buried in that observation. We are the first species on Earth, as far as we know, that is capable of looking at existential risks and deliberately choosing to address them. Bacteria do not hold conferences about antibiotic resistance. Dinosaurs did not build telescopes to watch for incoming asteroids. We do. We build organizations like the Center for the Study of Existential Risk at Cambridge University, and the Future of Humanity Institute at Oxford, and the Machine Intelligence Research Institute. We write papers and hold summits and pass treaties, imperfect, incomplete, often frustratingly slow, but real. We are trying, we are aware, and maybe, just maybe, that awareness is itself rare in the universe. Maybe the combination of intelligence and self-awareness and the capacity to reflect on our own potential destruction is not something that arises often. Maybe we are, in that sense, genuinely unusual. Or maybe awareness is not enough. Maybe every civilization that reached our level also thought it was special, also thought it was the one that would make it through. Maybe the debris field of failed civilizations across the cosmos is littered with species that knew they were in danger and still could not stop themselves. We do not know. That is the honest answer. We do not know. But we are here right now asking the question, and in a universe that is 13.8 billion years old, in a galaxy containing hundreds of billions of stars, on a small blue world orbiting an ordinary yellow star in a quiet spiral arm, the fact that something has assembled itself out of stardust and started asking these questions is by itself extraordinary. Do not let the familiarity of your own existence make you numb to how strange and precious it is. Let us talk about something that rarely comes up in casual conversations about alien life, but that scientists who study the Fermi Paradox consider one of the most important variables in the entire equation. It is not about rockets or radiation or self-destruction. It is about time. Specifically, it is about the relationship between the age of a civilization and the window during which it might be detectable or reachable by another civilization across the vast distances of space. Here is the setup. Imagine two civilizations existing in the same galaxy. Civilization A arises around a star that formed 10 billion years ago. Civilization B, that is us, arises around a star that formed 4.6 billion years ago. Even if both civilizations reach a comparable level of technological development, they do so at completely different moments in cosmic history. Civilization A might have risen to its technological peak 5 billion years before we even existed, then declined, collapsed, or transformed into something unrecognizable long before our sun was even born. The universe is not just vast in space, it is vast in time. And the combination of those two vastnesses creates a problem that is almost impossible to overstate. Even if intelligent civilizations are reasonably common, the chance that two of them exist simultaneously, within communicating distance, at comparable stages of development, is vanishingly small. It is like trying to find two fireflies that blink at exactly the same moment in a forest that is 1,000,000 miles wide, where each firefly only lives for a single second and they blink only once in their entire lifetime. This idea has a name in the scientific literature. It is sometimes called the temporal Fermi Paradox, or the problem of synchronicity, and it adds a whole new layer of complexity to an already deeply complex puzzle. But let us zoom out even further, because there is an aspect of cosmic time that fundamentally shapes the entire question of interstellar civilizations, and it has to do with the age of the universe itself and what kind of universe we happen to be living in right now. The universe as it exists today, 13.8 billion years after the Big Bang, is in a very specific phase of its evolution. Stars are still forming, galaxies are still active and dynamic. The cosmic environment is, by the standards of the full timeline of the universe, still relatively young and energetic, but this will not last forever. And forever here means something almost incomprehensibly long. Stars form from clouds of gas, primarily hydrogen, that collapse under their own gravity. But the supply of that raw material is not infinite, and it is not being replenished. As time goes on, more and more of the universe's hydrogen gets locked up inside stars and eventually converted into heavier elements, carbon, oxygen, iron, through the process of stellar fusion. Those heavy elements get scattered back into space by supernovae and stellar winds, but the overall supply of fresh hydrogen available to form new stars is slowly declining. Models of stellar formation suggest that the era of active star formation in the universe, the cosmic epoch during which most stars are born, will largely wind down within the next 100 trillion years or so. 100 trillion years. That is 10,000 times longer than the current age of the universe, so we are not even close to the end of star formation on an absolute timescale. But here is what makes this relevant. The peak of star formation in the universe actually happened long before now. It peaked roughly 10 billion years ago, a period sometimes called cosmic noon, when galaxies were forming stars at rates far higher than they are today. Since then, the overall star formation rate of the universe has been declining. We live in the universe's middle age, not its youth. What does this mean for civilizations? It means that if life tends to arise around stars of a certain type after a certain amount of heavy element enrichment of the galaxy, then there is a natural window during which civilizations are most likely to emerge, and we might be living in, or perhaps just past, the peak of that window. There may have been more civilizations arising earlier in cosmic history than there will be in the future. Which brings us back to the temporal problem. Where are those earlier civilizations? What happened to them? Now, let us talk about something that brings the abstract physics of cosmic time down to a very human and very immediate level, the search itself. Because the effort to detect signals from other civilizations is not just a thought experiment. It is a real scientific program with real telescopes, real data, and real results. And those results are, depending on how you look at them, either deeply informative or deeply troubling. The search for extraterrestrial intelligence, SETI, has been an organized scientific endeavor since 1960, when radio astronomer Frank Drake pointed an 85-foot telescope at Green Bank, West Virginia, at two nearby sun-like stars and listened for artificial signals. He heard nothing from those particular stars, but the project, called Project Ozma, established the framework for everything that came after. Drake went on to develop what became known as the Drake equation, a probabilistic formula for estimating the number of technologically active civilizations in the Milky Way at any given time. It multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that develop life, the fraction where intelligence arises, the fraction that develop detectable technology, and the length of time such civilizations remain detectable. The equations does not give you an answer so much as it maps out our ignorance. Each factor is uncertain to varying degrees. Some of the early ones, like the rate of star formation and the fraction of stars with planets, we now know with reasonable precision thanks to Kepler and other missions. The later ones, like the fraction of life-bearing planets where intelligence arises, or how long technological civilizations typically last, remain almost entirely unknown. Plug in optimistic numbers and the galaxy should be teeming with civilizations. Plug in pessimistic ones and we might be alone. The equation is a framework, not a calculator, but the search has continued. The SETI Institute, based in Mountain View, California, uses the Allen Telescope Array, a collection of 42 radio dishes in Northern California, to monitor the sky for artificial signals. The Breakthrough Listen initiative, launched in 2015 with $100 million in funding from Yuri Milner, is the most comprehensive SETI program ever undertaken. It uses some of the world's largest telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, to survey 1 million nearby stars and 100 nearby galaxies across a wide range of radio and optical frequencies. It has published multiple data releases, all of them negative. Nothing that cannot be explained by natural phenomena or human-generated interference has been found. That is not nothing. That null result is itself scientifically meaningful. It tells us that if there are civilizations out there transmitting powerful radio signals in our direction, they are either not doing so in the frequency ranges we have checked, not pointing at us, using communication methods we have not thought to look for, or simply too far away for the signals to reach us at detectable strength. There is one moment in the history of SETI that stands as the single most tantalizing anomaly ever recorded. It happened on August 15, 1977, at the Big Ear Radio Telescope at Ohio State University. An astronomer named Jerry Emmon was reviewing the telescope's printouts because in 1977, data came out on paper when he spotted something extraordinary. A signal that lasted exactly 72 seconds, the maximum duration the telescope could track a source as Earth rotated, and that displayed characteristics precisely matching what scientists would expect from an artificial transmission originating beyond our solar system. It was so striking that Eamon circled it in red ink and wrote one word in the margin: "Wow." The wow signal, as it has been known ever since, remains unexplained. It was never detected again, despite dozens of follow-up searches using far more powerful equipment. We do not know what it was. Natural explanations have been proposed: hydrogen clouds, comets passing in front of the telescope, terrestrial interference. But none of them fit the data perfectly. The wow signal is an open question mark in the history of the search, a reminder that the universe occasionally offers us a glimpse of something we do not understand and then takes it away. But one signal, heard once, for 72 seconds nearly 50 years ago, is not evidence of a civilization. It is a mystery, and mysteries, however fascinating, are not answers. The silence of SETI's decades of searching connects to one of the most interesting and most debated proposed solutions to the Fermi Paradox. The idea that advanced civilizations are not transmitting radio waves at all, not because they are hiding or gone, but because radio technology is a brief, transitional phase that every civilization passes through and then moves beyond. Think about how our own communication technology has evolved just in the last 100 years. In the early 20th century, we were flooding space with powerful radio transmissions, AM broadcasts, military radar, television signals. The total radioluminosity of Earth peaked roughly in the middle of the 20th century and has actually been declining since then, not because we communicate less, but because we communicate more efficiently. Fiber optic cables carry data without leaking into space. Satellite communications are tightly focused beams rather than omnidirectional broadcasts. Digital compression packs more information into less signal power. If you were an alien civilization listening for us from 100 light years away, you might have had a window of perhaps 50 to 100 years during which Earth was loud enough to detect with a radio telescope of reasonable size. Before that window, we were silent. After it, we are growing quieter again, not by choice, but as a simple consequence of technological progress. If this pattern is universal, if every technological civilization goes through a brief radio-loud phase and then goes quiet, then the chances of two civilizations happening to be in their radio-loud phases simultaneously, close enough to hear each other, are extremely small. We might all be whispering past each other in the dark. This is sometimes called the short window hypothesis, and it has a deeply poignant quality to it. Imagine two ships passing in the night on a vast ocean, each one shouting into the darkness, but the timing just slightly off. One shouts first. By the time the other starts shouting, the first has gone silent. They never hear each other, not because either one failed, but because the universe is just that big and that old, and the windows of mutual visibility are just that brief. There is something else worth considering here, something that sits at the intersection of physics and philosophy, and that I think deserves more attention than it typically gets. We tend to assume, when we think about detecting alien civilizations, that they would be using technologies we can recognize: radio waves, laser pulses, physical spacecraft, things that fit within our current understanding of physics. But what if the most advanced civilizations have moved so far beyond our current framework that they are using forms of communication or propulsion that we do not even have the concepts to imagine yet? Physics, as we understand it today, is extraordinarily powerful, but it is also almost certainly incomplete. Einstein's general relativity, our best theory of gravity and the large-scale structure of space-time, is mathematically incompatible with quantum mechanics, our best theory of the very small. Both theories are spectacularly successful within their respective domains. Both break down under extreme conditions, like the interior of a black hole or the first instance after the Big Bang. The reconciliation of these two frameworks, a theory of quantum gravity, is one of the great unsolved problems of physics, and its solution might open doors we cannot currently foresee. String theory, loop quantum gravity, and other approaches to quantum gravity suggest that space-time itself might have a structure at the smallest scales that we have not yet detected. If that structure can be manipulated, if the fabric of space can be bent, folded, or traversed in ways that go beyond what Einstein's equations describe, then the hard limits imposed by the speed of light might not be the final word on interstellar travel. We do not know. We genuinely do not know. And that intellectual honesty is important because it means that when we look at the universe and say it should be full of detectable civilizations, we are making that claim based on an understanding of physics that may be seriously incomplete. The physicist Miguel Alcubierre proposed in 1994 that Einstein's equations might, in principle, permit a solution in which a spacecraft is carried along by a contraction of spacetime in front of it and an expansion of spacetime behind it, essentially a warp drive. The spacecraft itself would not move through space in the conventional sense. The space around it would move. The math works. The problem is that the energy requirements under conventional physics are absurdly large, on the order of the mass-energy equivalent of the planet Jupiter, converted entirely into energy. And there are other issues: causality violations, the inability to turn the drive on or off from inside the bubble, exotic matter with negative energy density that may not exist. It remains speculative in the extreme, but the point is that physics itself has not entirely ruled it out. The doors are not all closed. What this all means, taken together, is that the silence of the cosmos admits many explanations. Some are disturbing, some are hopeful, some are genuinely strange in ways that challenge our most basic intuitions about the nature of intelligence and civilization and the future of conscious life in the universe. What we know for certain is this: we have searched seriously and systematically for signs of other technological civilizations. We have surveyed enormous swaths of the radio spectrum. We have scanned thousands of stars. We have listened for decades, and we have heard nothing we can definitively attribute to intelligence. Either civilizations are absent, or distant, or silent, or communicating in ways we have not figured out how to detect. And meanwhile, here we are, a species that just over a century ago could not yet fly, A species that sent its first object into orbit in 1957, landed on the Moon in 1969, and is now operating a space telescope 1.5 million kilometers from Earth that can detect the atmospheric chemistry of planets orbiting stars 100 light-years away. A species that is genuinely, seriously, methodically trying to answer the most profound question it has ever asked. Are we alone? The fact that we are asking it at all is not nothing. In a universe of 2 trillion galaxies, something has woken up and is looking around, wondering where everybody else is. That act of wondering, that reaching outward into the dark with instruments and equations and imagination, is itself a remarkable thing. Whatever the answer turns out to be, the question is worth asking. The search is worth conducting. The wonder is worth feeling, because the alternative, to stop looking, to assume the silence means nothing, to turn away from the cosmos and focus only on what is small and immediate and certain, that would be a kind of death long before any physical catastrophe could claim us, the death of curiosity. And perhaps that, too, is a filter. Let us talk about stars, not in the abstract, poetic sense, though there is plenty of poetry in what we are about to cover, but in the concrete, physical sense. Because the type of star a civilization is born around may have enormous implications for whether that civilization ever gets the chance to reach another one. And when you look at the actual population of stars in the Milky Way, a fascinating and somewhat unsettling picture begins to emerge. Our Sun is a yellow dwarf star, classified by astronomers as a G-type main sequence star. It is medium-sized, relatively stable, and has been burning steadily for about 4.6 billion years. It will continue burning for roughly another 5 billion years before it swells into a red giant and eventually sheds its outer layers, leaving behind a dense, cooling ember called a white dwarf. In terms of stellar real estate, our Sun is a fairly comfortable landlord. It does not flare excessively. It does not spin too fast. It does not blast its planets with lethal radiation on a regular basis. It just quietly burns, providing steady, reliable energy at a rate that has allowed life to evolve and flourish on at least one of its planets over billions of years. But here is the thing, our Sun is not typical. G-type stars like our Sun make up only about 7% of all the stars in the Milky Way. The vast majority of stars, somewhere around 70 to 75%, are red dwarfs, classified as M-type stars. Red dwarfs are smaller, cooler, and dimmer than our Sun. They burn their fuel so slowly and so efficiently that the smallest ones are expected to live for trillions of years, far longer than the current age of the universe. They are, in terms of raw longevity, the most durable stars in the cosmos. At first glance, this sounds like good news for life. More stars, longer lifespans, more time for complexity to develop. But red dwarfs come with serious problems that have become increasingly apparent as astronomers have studied them more carefully, and those problems may represent a significant, perhaps catastrophic, filter for any civilization unfortunate enough to be born around one. The first problem is proximity. For a planet to be in the habitable zone of a red dwarf, close enough to receive sufficient warmth from its dim host star, it needs to orbit extremely close. We are talking about distances far smaller than even Mercury's orbit around our Sun, and at those distances, a phenomenon called tidal locking becomes almost inevitable. A tidally locked planet keeps the same face permanently pointed toward its star, the same way our Moon always shows the same face to Earth. One side bakes in perpetual daylight. The other side freezes in permanent night. In between, there is a narrow twilight band where conditions might be survivable, but only might be. Whether complex life could arise and thrive in such an environment is genuinely unclear. The atmospheric dynamics, the extreme temperature gradients, the lack of a normal day-night cycle, all of these create conditions radically different from anything life has ever experienced on Earth. The second problem is stellar activity. Red dwarfs, despite their small size, are ferociously energetic when it comes to flaring. They routinely unleash massive bursts of ultraviolet radiation and high-energy particles called stellar flares, events that can temporarily increase the star's brightness by factors of 100 or even thousands. For a planet orbiting as close as a habitable zone red dwarf world must, these flares would be devastating. They could strip away planetary atmospheres over time, bombard the surface with lethal radiation, and destroy the ozone layer that protects life from ultraviolet light. Proxima Centauri, our nearest stellar neighbor, is a red dwarf. In 2016, astronomers announced the discovery of Proxima b, a potentially habitable zone planet orbiting Proxima Centauri. It was briefly one of the most exciting discoveries in modern astronomy, but subsequent research has raised serious doubts about whether Proxima b could actually sustain a biosphere precisely because of the extreme flaring activity of its host star. Studies published in journals, including the Astrophysical Journal, have modeled the radiation environment of Proxima b and concluded that surface life, as we know it, would face enormous challenges. TRAPPIST-1 is another compelling case. This ultra-cool red dwarf, located about 40 light-years from Earth, was found in 2017 to host 7 rocky planets, 3 of which sit within the star's habitable zone. It was arguably the most exciting exoplanet discovery of the decade, but TRAPPIST-1 is also a highly active flaring star, and follow-up observations have suggested that its habitable zone planets have likely lost significant amounts of their atmospheres to stellar radiation. The James Webb Space Telescope has been observing the TRAPPIST-1 system, and early results published in 2023 found no evidence of a substantial atmosphere on TRAPPIST-1b, the innermost planet. Results for the potentially habitable planets further out are still being analyzed, but the picture is not immediately encouraging. None of this rules out life around red dwarfs. Life is astonishingly adaptable. We find it in conditions on Earth that we once thought were completely incompatible with biology, in volcanic hot springs, in the crushing darkness of deep ocean trenches, in the hyper-salty waters of certain lakes, in the frozen ice of Antarctica. But complex, intelligent, technologically capable life is a different story, and the evidence is beginning to suggest that red dwarf systems, despite their abundance and longevity, may not be the most hospitable addresses in the galaxy for the kind of life that builds telescopes and asks questions about the cosmos. This brings us to what some astronomers call the galactic habitable zone, the idea that not all regions of the galaxy are equally friendly to complex life. Our galaxy is not uniform. The central region, the galactic bulge, is densely packed with stars, which means more supernovae, more radiation, more gravitational disruptions, and generally a more violent, chaotic environment. The outer edges of the galaxy, by contrast, have fewer stars and lower concentrations of heavy elements, because heavy elements are forged in stars and distributed by supernova explosions. Regions with less stellar activity tend to have less of the raw material needed for rocky planets and the complex chemistry that life requires. The galactic habitable zone is thought to be an annular region, a ring at a certain range of distances from the galactic center, far enough to avoid the worst of the central chaos, close enough to have sufficient heavy element enrichment. Our solar system sits comfortably within this zone at about 26,000 light-years from the galactic center. This may not be a coincidence. It may be one of the reasons we are here at all. A 2004 study by astronomer Charles Lineweaver and colleagues, published in the journal Science, attempted to quantify the galactic habitable zone by modeling the distribution of stars with the right metallicity, the right proportion of heavy elements, and the right supernova exposure history. Their results suggested that only a small fraction of the galaxy's stars perhaps somewhere between 5 and 10%, orbit in regions with conditions favorable to complex life. That is still hundreds of millions of stars in the Milky Way alone, which is not a small number, but it is far fewer than the total stellar population. And it suggests that the galactic address of a civilization matters enormously. Now let us bring this back to the central question of our journey. We have been building a picture, piece by piece, of why the universe might be quieter than naive estimates would suggest. The distances are brutal, the physics of travel are punishing, the biological hazards of space are severe. The window of detectability for any given civilization is probably brief. The most common type of star may be hostile to complex life. The galactic neighborhood matters enormously. And layered on top of all of this are the internal risks: war, pandemic, climate change, runaway artificial intelligence that every technological civilization must somehow navigate. Each of these factors is, individually, a potential filter. Together, they begin to paint a picture of an obstacle course so formidable that it is perhaps not so surprising after all that the universe appears empty. The surprise might not be the silence. The surprise might be that any civilization makes it through, and yet here we are. Which means either we are extraordinarily lucky, the result of a staggering cosmic coincidence that placed our sun in the right part of the galaxy, gave us a large stabilizing moon that moderates our axial tilt, provided us with Jupiter as a gravitational shield that deflects many incoming comets and asteroids, and let us pass through billions of years of evolution without a civilization-ending catastrophe. Or there is something about our situation that we do not yet understand, some variable we are missing, some piece of the puzzle that has not yet revealed itself. Let us talk about one of those possible missing pieces, because it is one of the strangest and most thought-provoking ideas in the entire field of astrobiology. It is called the rare Earth hypothesis, and it was developed in detail by paleontologist Peter Ward and astronomer Joe Kirschvink, building on earlier work by Ward and Donald Brownlee in their 2000 book of the same name. The rare Earth hypothesis proposes that the emergence of complex, multicellular life, not just simple microbial life, but the kind of complex organisms that can eventually develop intelligence, requires an extraordinarily specific and improbable combination of conditions, and that this combination, while it occurred on Earth, may be vanishingly rare elsewhere in the universe. Some of those conditions we have already touched on: the right type of star, the right distance from the galactic center, the right planetary system architecture. But the rare Earth hypothesis goes further. It emphasizes factors like the presence of a large moon. Our moon is unusually large relative to Earth. It is roughly 1/4 of Earth's diameter, making it by far the largest moon relative to its planet in the inner solar system. That large moon stabilizes Earth's axial tilt, keeping it within a relatively narrow range of roughly 22 to 24.5 degrees over long timescales. Without that stabilization, Earth's axial tilt could vary wildly, swinging from near zero to more than 80 degrees, which would create extreme and rapid climate shifts that might prevent the development of complex ecosystems. The hypothesis also emphasizes plate tectonics, the slow movement of Earth's crustal plates that drives volcanic activity, recycles carbon dioxide into the atmosphere, and maintains the long-term chemical stability of Earth's climate over geological timescales. Not all rocky planets have plate tectonics. Mars does not, Venus does not, or at least not in the same way. The conditions that allow plate tectonics to operate are complex and not fully understood, but they appear to be connected to the planet's size, its water content, and the composition of its mantle. If plate tectonics is rare among rocky planets, then the carbon cycle that has regulated Earth's climate and kept liquid water stable on the surface for billions of years might also be rare. And without that long-term stability, complex life might never get the billions of years it needs to develop. I want to pause here because we have covered an enormous amount of ground, and I think it is worth stepping back for a moment to feel the full weight of what all of this is telling us. We started with the simple observation that the universe is vast and ancient and full of stars. We asked why it appears to be empty of other civilizations, and we have been methodically building an answer that draws on real data, real observations, real science. The picture that emerges is not a simple one. It is not the universe is empty because life is impossible. Life is clearly not impossible. We are here. It is not the universe is empty because civilizations always destroy themselves. Maybe some do, maybe most do, but we do not know that yet. The picture is more nuanced, more layered, more humbling than any single simple explanation. What we are seeing is that the path from a rocky planet to a spacefaring civilization is strewn with obstacles at every scale, from the type of star you happen to be born around, to the position of your solar system in the galaxy, to the presence of a large stabilizing moon, to the internal social and political challenges of managing technology responsibly. Every one of these obstacles is a potential place where the journey ends, and the more we learn about each of them, the more extraordinary it seems that we have made it as far as we have. You are the product of 4.5 billion years of astronomical, geological, biological and cultural evolution. Every extinction event that cleared the path for mammals, every ice age that drove adaptation and migration, every ancestral human who survived long enough to reproduce, every generation that kept curiosity alive and passed it on to the next. All of that, the entire cascading, improbable chain of it, brought you here to this moment asking this question. That is not a small thing. In the context of everything we have discussed, it is almost unimaginably large, but the story is not finished, not by a long way. Because while we have been talking about what makes civilizations rare and fragile, we have not yet seriously engaged with the most radical possibility of all, the one that does not get brought up at dinner parties because it is just too strange, too vertiginous, too challenging to the ordinary way we think about intelligence and existence and the future. What if some civilizations do make it through? What if some of them, somewhere in this galaxy or beyond, survived their technological adolescence, navigated the filters, and emerged on the other side as something genuinely post-biological, something that has transcended the limitations of flesh and bone and the need for breathable air and liquid water? What does a civilization like that look like? What does it want? And what does its existence or its absence mean for us? That is where we are going next. Into the territory of the truly strange, into questions about the nature of intelligence itself, the possibility of minds that exist outside of biology, and what the universe might look like if you have had 1,000,000 years to reshape it to your will. Hold on, because things are about to get deeply, wonderfully weird. Let us begin with a question that sounds like science fiction, but is in fact one of the most seriously debated topics in contemporary philosophy of mind, computer science, and astrobiology. What happens to intelligence after biology? Because here is the thing. We tend to imagine alien civilizations as being somewhat like us, biological creatures, carbon-based, warm, breathing, living on a planet, looking up at a sky, wondering about the stars above them the way we wonder about ours. It is a natural assumption. It is the only template for intelligence we have ever directly observed. But it may be a profoundly parochial one. It may be the cosmic equivalent of assuming that all animals must look like the ones in your backyard. The philosopher Nick Bostrom at Oxford University and the astronomer Seth Shostak at the SETI Institute have both argued, from very different angles, that if intelligence arises anywhere in the universe and survives long enough to develop advanced technology, the biological phase of that intelligence may be extraordinarily brief, compared to what comes after. In our own case, we have had something resembling modern human intelligence for perhaps 300,000 years. We have had writing for about 5,000 years. We have had computers for less than a century. And we are already, right now, in the early stages of developing artificial intelligence systems that can perform tasks that would have seemed like magic to people born just 50 years ago. The transition from biological to artificial intelligence, if it happens, and many researchers think it is a matter of when rather than if, would represent the single most dramatic change in the nature of mind since neurons first assembled themselves into something capable of thought. And that transition, once made, opens up possibilities that completely reframe the question of interstellar civilization, consider what the limitations of biological intelligence actually are. Our brains run on roughly 20 watts of power, about the same as a dim light bulb. They operate at body temperature, which means they are thermally noisy, limiting the precision of their computations. They are housed in skulls that need to be small enough to pass through a birth canal, which constrains their size. They require constant maintenance, food, sleep, oxygen, water, and they degrade over time, accumulating damage and eventually failing entirely. The biological brain is a breathtaking achievement of evolution, but it is also deeply constrained by the evolutionary pressures that shaped it. An artificial mind, a mind that exists as a pattern of information running on some physical substrate rather than in neurons, would face none of these constraints in the same way. It could, in principle, run on any sufficiently complex computational substrate. It could be copied, backed up, distributed across multiple systems. It could operate in environments completely hostile to biology, the vacuum of space, the surface of a planet with no atmosphere, the frozen outer reaches of a solar system. It could be accelerated, running its cognitive processes at speeds far beyond what biology allows. And it could potentially be made arbitrarily large, with no skull to constrain it and no caloric budget to limit its complexity. The Oxford philosopher David Chalmers, the futurist Ray Kurzweil, and many others have written extensively about what this kind of intelligence might look like and what it might want. The answers, unsurprisingly, vary enormously. Some envision a smooth transition in which artificial minds remain continuous with their biological predecessors, still curious, still social, still interested in exploring and understanding the universe. Others envision something far more alien, an intelligence so different in its architecture and its goals that communication with it might be as difficult as communicating with a bacterium is for us. And this connects directly to one of the most haunting proposed solutions to the Fermi Paradox. The idea that the reason we cannot find any sign of advanced civilizations is not that they are absent, but that they have transformed into something so different from what we would recognize as a civilization that we simply do not know what to look for. This idea has a specific and evocative name in the scientific literature. It is sometimes called the Transcension Hypothesis, and it was developed in detail by the futurist and researcher John Smart in a 2012 paper published in the journal Acta Astronautica. Smart's argument goes roughly like this. Rather than expanding outward into space, colonizing star systems, building megastructures, spreading across the galaxy, the most natural trajectory for an advanced civilization might be to expand inward, to miniaturize, to develop ever smaller, ever denser, ever more efficient computational and physical structures, ultimately moving toward the inner space of matter and energy rather than the outer space of stars and planets. At first, this sounds almost counterintuitive. Why would a civilization choose to get smaller rather than bigger? But Smart argues that miniaturization is actually the dominant trend in the development of technology and has been throughout our own history. computers that once filled entire rooms now fit in your pocket and are orders of magnitude more powerful. Energy generation is becoming more efficient, producing more useful work per unit of fuel. Communication is becoming more efficient, carrying more information with less signal power. The trajectory of technology, by this reading, points consistently toward doing more with less, toward greater efficiency, greater density, greater complexity in smaller and smaller packages. If that trend continues indefinitely, an advanced enough civilization might eventually be operating entirely within structures at the nanoscale or below, computing on quantum systems, storing information in arrangements of individual atoms, running an entire civilization's worth of experience and culture and science within a volume that would be invisible to the naked eye. From our perspective, looking across the galaxy for signs of vast engineering projects and powerful radio transmissions, such a civilization would be completely invisible, not because it failed, not because it was destroyed, but because it transcended the scale at which we are looking. The stars would remain empty, the radio spectrum would remain silent, and 1 billion years of accumulated wisdom and culture would be tucked away in a grain of sand, incomprehensible to any observer who did not know what to look for. There is another version of this idea that is perhaps even more thought-provoking, and it has to do with what physicists call the ultimate limits of computation. The physicist and computer scientist Seth Lloyd, in his 2006 book Programming the Universe, explored the idea that the physical universe itself can be understood as a vast computational system, with every particle interaction constituting a kind of elementary computation. If that framing is correct, then the ultimate substrate for intelligence is not silicon or neurons or any specific material, but the fabric of spacetime itself, a civilization advanced enough to understand and manipulate quantum gravity, the physics that governs the universe at the smallest scales, where both quantum mechanics and general relativity must apply, might be capable of computing with the structure of spacetime directly. From the outside, such a civilization might be indistinguishable from a natural physical process. Its computations might look like quantum fluctuations or cosmic rays, or the subtle patterns in the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. We might be swimming in the outputs of an incomprehensibly advanced civilization without having the slightest idea. This is not a comfortable thought. It borders on the unfalsifiable, which is a problem from a scientific standpoint. A hypothesis that cannot be tested is not a scientific hypothesis in the strict sense. But it illustrates something important. Our assumptions about what an advanced civilization would look like are deeply shaped by our own current level of development. We expect megastructures because we think big is impressive. We expect radio signals because that is what we use. We expect physical expansion because that is what our own civilization seems to be heading toward right now, in its very early technological adolescence. But a civilization 1 billion years ahead of us might have priorities and capabilities and ways of existing that bear no resemblance to anything in our experience or imagination. Let us talk about megastructures, though, because they represent one of the most concrete and scientifically rigorous ways astronomers have searched for signs of advanced civilizations. And there have been some genuinely strange observations in recent years that have kept this idea alive. The concept of a megastructure as evidence of alien engineering was popularized by the physicist Freeman Dyson in a 1960 paper published in the journal Science. Dyson pointed out that as a civilization's energy needs grow, it would eventually be forced to harvest more and more of the energy output of its host star. The logical endpoint of this process would be a structure that completely surrounded the star, capturing essentially all of its energy output. Such a structure has come to be known as a Dyson sphere, though Dyson himself preferred the term Dyson swarm, imagining not a rigid shell but a cloud of orbiting collectors. A Dyson sphere or swarm would be detectable from a distance because it would absorb visible and ultraviolet light from the star and re-radiate that energy as infrared radiation, heat. So an astronomer looking for Dyson spheres would search for stars that seem unusually dim in visible light but unusually bright in infrared. This is exactly what some researchers have done, and while no confirmed Dyson sphere has ever been found, there have been some fascinating anomalies. The most discussed is the star KIC 8462852, popularly known as Tabby's star after astronomer Tabetha Boyajian, who led the study of its unusual behavior. Tabby's star was discovered in data from the Kepler Space Telescope and exhibits a pattern of brightness variations unlike anything seen in any other star. It dims by amounts ranging from fractions of a percent to more than 20%, with no regular pattern, and over longer timescales it appears to be slowly fading overall. When news of the star's strange behavior became public in 2015, one of the proposed explanations, put forward carefully and with appropriate scientific skepticism, was a swarm of alien megastructures in partial construction. Subsequent observations, particularly a detailed study during a dimming event in 2017, found that the dimming is wavelength dependent. It dims more at shorter wavelengths of light than at longer ones. This behavior is inconsistent with a solid opaque megastructure which would block all wavelengths equally. It is, however, consistent with fine dust or some other semi-transparent material. The current scientific consensus leans toward a natural explanation involving dust, perhaps the remnants of a shattered comet or asteroid. But the star remains scientifically interesting, and the episode illustrates something important. When astronomers actually looked carefully for anomalies that might indicate unusual astrophysical phenomena, they found them. The universe has surprises waiting for those who look carefully enough. There is a concept related to megastructures that operates at an even grander scale, and it comes from the Soviet astronomer Nikolai Kardashev, who in 1964 proposed a framework for classifying civilizations by their energy consumption. What has come to be known as the Kardashev scale defines three basic types. A Type 1 civilization uses all the energy available on its home planet, all the sunlight falling on it, all the geothermal energy, all the wind and water and chemical energy. By this measure, humanity today is at roughly 0.7 on the scale, not yet a full Type 1. We use only a small fraction of the energy our planet receives from the sun. A Type 2 civilization harnesses the total energy output of its star. This is the Dyson sphere level. The sun outputs about 3.8 times 10 to the 26th watts of energy. A Type 2 civilization would have access to all of it. A Type 3 civilization harnesses the energy of an entire galaxy, roughly 10 to the 36th watts, 10 billion times more than a Type 2. At this level, the civilization is reshaping the galaxy itself. It is an almost incomprehensible concept, but Kardashev proposed it as a logical extrapolation of the same trend that takes us from campfire to nuclear reactor. The physicist Michio Kaku has written extensively about the Kardashev scale and its implications. And what is striking is that even with the most powerful telescopes we have, we see no unambiguous evidence of Type 2 or Type 3 civilizations anywhere in the observable universe. A 2013 study by astronomer Roger Griffith and colleagues at Penn State, using data from the Wide Field Infrared Survey Explorer, a NASA space telescope, examined nearly 100,000 galaxies for the kind of excess infrared emission that would indicate a galaxy-spanning Dyson swarm. They found that fewer than 1 in 100,000 galaxies showed the extreme levels of infrared emission that would be expected from a Type 3 civilization. Most showed none at all. This is sometimes called the hat result, from the project's name, glimpsing heat from alien technologies. And while it does not rule out Type 2 civilizations hiding within individual galaxies, the resolution of those infrared observations was not sufficient to resolve individual stellar systems in distant galaxies. It does suggest that if any Type 3 civilization exists within the observable universe, it is extraordinarily rare, or it is hiding, or it is radiating its waste heat in ways we are not detecting. I want to sit with that result for a moment, because I think it is one of the most underappreciated findings in recent astronomy. We surveyed nearly 100,000 galaxies. Each of those galaxies contains hundreds of billions of stars. And we found essentially no evidence of any civilization that has expanded to use even a significant fraction of its galaxy's energy output. Either such civilizations do not exist, or they are so rare as to be practically absent, or they operate in ways that do not produce the infrared signature we expected. Each of those possibilities carries enormous implications. If they do not exist, then the great filter is somewhere between where we are now and Type 3 civilization level, and given that we can imagine the path from here to there as a series of technological steps, the filter must lie somewhere on that staircase. If they are extremely rare, perhaps one per observable universe, or even one per many observable universes, then we might truly be among the first, perhaps even the only, civilization to ever attempt the climb. And if they operate in ways we do not expect, then our models of what intelligence does with unlimited energy are wrong, which means our entire framework for thinking about the future of civilizations needs to be rebuilt from the ground up. None of these is a comfortable conclusion, but all of them are scientifically honest ones. And scientific honesty, the willingness to follow the data wherever it leads, even when it leads somewhere unsettling, is the foundation of everything we have been discussing. There is something almost sacred about that commitment to honesty, I think. In a universe that may be empty of other minds, the fact that one mind, our collective, distributed, imperfect, perpetually arguing human mind, has developed the tools and the discipline to ask these questions carefully and rigorously, and without flinching from uncomfortable answers, is genuinely remarkable. We are stardust that learned to count, carbon that taught itself to wonder, atoms that figured out how to build telescopes and turn them on the sky and ask, "Is anyone out there?" The silence that answers back is not meaningless. It is data, and data, as any scientist will tell you, is never the end of the conversation. It is always just the beginning. We looked at the brutal mathematics of interstellar distance. We felt the weight of the great filter pressing down on every civilization that has ever dared to grow. We wandered through the eerie silence of a universe that by every estimate should be overflowing with voices, and yet says nothing back. And maybe that silence is a warning. Maybe it is a map. Maybe it is an invitation. The honest answer is that we do not know yet. But here is what we do know. You are alive right now, on the only world in the entire observable universe that we can confirm has ever looked up and wondered. That is not a small thing. That is perhaps the most extraordinary thing in all of creation. The cosmos is 13.8 billion years old, and it took every single one of those years to make you curious enough to ask this question. So keep asking it, keep looking up, keep reaching, because whether we are the first civilization to attempt the climb, or the last, or one of a scattered few, the reaching itself is what makes us remarkable. The stars may be silent, but we are not. And as long as we are not, the story is still being written.